Hello all. So today we are going to design a heat exchanger with the help of a software Aspen exchanger designing and rating. So like Aspen Plus and Aspen Hysys, there is another tool, or we can say the software known as Aspen exchanger design and rating. So right now I am going to use the version 9. Okay. So in this exercise what we are going to do is, first of all, we will design, with the help of shortcut method, we will say that we are going to raise a temperature of a cold fluid from 20 degrees Celsius to 40 degrees Celsius to 40 degrees Celsius. Later on, in order to get this, in order to have this, we will have to have a heat exchanger, and we are going to have a geometry of a heat exchanger. Geometry of a heat exchanger based on this shortcut method designed heat exchanger. Now we know that industrial standards are something different than a real calculated design spec. For example, you may get a tube size of 20 mm in reality by calculating by hand calculation, that you may have a 20 diameter of a pipe, or the tube sufficient for sufficient to get from a fluid from 20 degrees Celsius to 40 degrees Celsius. But we know that in industry 20 is not a standard size. So what Aspen Plus or EDR, or we can say Aspen Exchanger design and rating software, will take this size to a nearby standard size, say 22 So I don't know whether 22 is a standard size or not, but let's assume 22 It will take it to this size. But what will happen with the help of this 22 we are not going to get 40 degrees Celsius exact. We may get, uh, instead of 40, we may get 45 degrees Celsius, etc. So later on, what we are supposed to do, we are supposed to adjust it. So in this exercise, I am not going to adjust it. I will keep it as it is. If it comes 40, at any other temperature, say other than any temperature of say 45 degrees Celsius itself, but we can adjust it with the help of design spec, which is a tool in Aspen Plus. And later on, once that is done, we are then we may say that the design or the exchanger geometry is finalized, and we can then use it. Either we can use it for the academicians, we can keep it for assignment, or in for the industries we can use it for fabrication. Okay, so let us start. So I have already opened Aspen Plus. How to open Aspen Plus? We can directly click Aspen Plus app here. We are not supposed to open Aspen Exchanger Designing and Reading, okay, because this comes automatically in Aspen Plus. How we will go, we will see it. Okay, then in properties, if I will go here, I have added water as a component because I want to put water in both shell and tube type, both shell and tube sites. Then I have just kept ideal method, but actually if water is there, I need to use an activity coefficient method, uh, say NRTL, etc. But just in order to keep it simple, I have chosen ideal method. Then I went to simulation environment. Okay, here I need to take one of the heat exchanger. So here I need to specifically take heat X, in which uh, two streams are generally taken, and most widely this particular block is used, right? So I'm taking it here. Okay, I am adding material streams. This one is cold required, so this is cold in, cold out. This is hot in and hot out. This is a simple way most of you may be knowing how to do a simple simulation. So I am increasing its size so that we can see it clearly. Okay. Now I can simulate it by clicking on next button. So next button is like, unlike Aspen Hysis, a next button is supposed to be pressed here. Okay. So temperature, so since it's S1 cold stream, say temperature is 20 degrees Celsius, pressure is 1 bar, moles are say 100 kilomoles an hour. Again here 100 kilomoles an hour. Okay. Click next button. Now this one is particularly S3. S3 is the hot stream. So S3 is, let's say, is coming at 80 degrees Celsius. 1 bar, moles, again assume 100 kilomole an hour, and again here 100. Okay. I can also okay, now it is actually going into this block B1. Here we know that first of all we need to design it with the help of shortcut method, but we know that this particular now problem is going to solve this particular equation. Q is equals to UA LMTD. Now we know uh, and again MCP delta T, right? These are the two equations which it is going to solve. Now this MCP delta T can be of any of the on any side, right? Q is equals to, these both Q's are same, right? So if I will give this give T1 minus T2, if I will specify this T1 and T2, then Cp, of course, it will come to know because it is function of temperature. Mass flow rate I have specified, so it will calculate Q, and LMTD is nothing but a so I can write it as a function of T1, T2, and T1 and T2, right? So we know T1 and T2 because I have just specified. I'm going to specify in shortcut method. Then only one of the thing is remain to be solved, right? Set T2 because T1 is a cold side temperature which is coming in, and T2 is the only thing which is remaining, right? So so since I'm specifying everything MCP T1 and T2 here, Q will be calculated, this Q will be put here, and now everything will be known, but only this particular value T2 will be unknown, and that will be calculated. So this is nothing but a simple calculation which is going to be done here in this particular shortcut fidelity model, right? Right. Okay. So I am specifying here cold stream outlet temperature, say 40 degrees Celsius. I will run it. Okay, results are out, and see 40 degrees Celsius. So I have instead of, so I should have, okay, here. So 100 moles are here and there in both of the sides, right? Hot temperature is going from 80 to 61 degrees Celsius to make this stream which is at 20 degrees Celsius to 40 degrees Celsius. Now on the basis of this, I want to get a geometry of this heat exchanger. So it is like a question, like if I have a heat exchanger which is taking a fluid from 20 degrees Celsius to 40 degrees Celsius with the help of a hot fluid which is at 80 degrees Celsius to 61 degrees Celsius. So please find the heat exchangers geometry. Okay, so again go in the setup here. Now this time click, instead of shortcut, click on the shell and tube. Now automatically this option, which is actually taking us to exchanger designing and rating, will come up. But I'm saying here I can either size heat exchanger from here itself, or I can specify heat exchanger geometry which is already built in. Now how to take this how to specify this geometry? We can use an uh, already designed heat exchanger, and that geometry and that every detail is stored in a file with the extension of EDR that just I showed you, Aspen Exchanger, in this particular app, right? Okay. So right now, what I'm going to do is I'm going to click on convert. See, now this thing come up. This is nothing but an option to. This is nothing but an option to convert that particular shortcut heat exchanger into more detailed one. Now we can see here by clicking on the process that flow rates and everything are mentioned here. We know that it's actually mass flow rate. So I cannot see, I don't think that I can see what are the mole flow rates, right? Now again I will go here. We know that most of the times it is nothing but the BEM type of the shell and tube, BEM type of the heat exchanger. So what is BEM? So this one shows me the tema designations. So B meaning bonnet, internal cover. E, this is very important, it is just a one pass shell, right? And M is fixed tube sheet. So that is there. So I'm going to use B, then E, and then M, right? I can also use any of the other two partial, long, baffle, etc. and etc. But just to keep it very simple, just one side shell pass, but tube passes can be multiple. So that is not the restriction. Okay, so I will just click on the size. But before that, if you want to specify something which you can also do some changes here. So here in this particular option, you can specify some of the sizes of the design. For instance, if I will click here, then I can specify tube length, or even I can specify how many number of tube passes. But you cannot specify number of tubes. Say, but many times you need just have one tube pass, then you can write one here, right? But right now I'm not going to use that. I will just click no, right? And I will quickly size it. Okay, sizing is done, and you can see that there are 1, 2, 3, 4, 5, 6 baffles. Now the hot fluid is coming from this one. This one is S1, which is written here. So here hot fluid is coming like this and getting out like this, and cold fluid is actually going. So see, the number of tube passes are 6 here. So it is like it is coming at this temperature, then going till this temperature, and going like this and this and this and that. You can just click here yes, and click here one pass, and you can size it again. See, now if you see the heat exchanger, so actually uh, this should have been one here. So there the baffles should not be this many here, because okay, sorry, you can see the nozzles. So this one is particularly T1 tube side in, which is coming here, and the fluid is going out here, right? And if you will see here the temperature, then it is coming at this temperature and going out at this temperature, right? And here again it's the hot side temperature. Now our exchanger is ready, and I can either accept it, or I can, in order to accept, I can just click here, or I can again change something and then size it, and finally I can do it. I can also save it particularly. So for instance, some of the times you may see that, okay, this particular design seems to be very okay, so I will save it with a particular name, and I can use it again to change, and I can again change something here, and again accept save that design with a particular other name, and I can see the performance of the heat exchanger by using that particular geometry in the simulation. So right now I am accepting this design, okay, and I am so now see on the status here the input is again changed, because right now the cold stream outlet temperature is not specified, right? The geometry is specified. So where is the geometry? You can just click here on the EDR browser, and you can see the geometry over here. So on the mechanical sheet, sorry, mechanical summary, you can see the setting plan, etc. But the stream outlet temperatures are not yet out. So I said that the temperature is going from 20 degrees Celsius to 40 degrees Celsius, but that is just the output of the design and not the simulation, not the current outlet, because now the simulation is run by this particular geometry. So I will now again run it. Now the heat exchanger is the simulation is based on this particular geometry, and you can see that the temperature now is not 40 degrees Celsius. The temperature is now at 46 degrees Celsius. Why? Because the geometry is very standard. You can of course decrease the number of tubes, etc. to see what is the effect. For instance, let us decrease the number of tubes, because the temperature is 46 degrees Celsius. But actually I wanted it to be uh, 40 degrees Celsius, right? So I can again click on this EDR browser, then I can again go here, exchanger geometry, then tubes, then instead of 51, because those are the number of tubes which we saw, right? So if you want to see, you can see, click here mechanical summary, we can see the tube sheet layout. You will see here that the number of tubes are 51, right? You can of course copy this geometry, say like this, copy, then paste it, sorry, paste it in paint or say PowerPoint. So meanwhile, okay, paste it here. You can see it clearly, right? Right. Number of 51, and these are supports, these are etc. rods and etc. and the number of tubes and arrangement etc. We can see these particular dash lines are nothing but the baffle, and the baffle cuts are all also given in this particular uh, output that can be seen here in many of the options. For instance, one of the option is tema sheet, and that tema sheet can also be extracted. Right here, everything will be given. Instead, what is the pressure drop and the design standard, that is ASME code section code, and section 8. You know it, division 1. That is very standard, right? And then we can also see the pressure drop within the system. For instance, the pressure drop, the inlet nozzle makes the inlet nozzle, right? Inlet nozzle and the inside tubes, etc. You can see that the pressure drop here is 0.26, just because of, so 68% of the pressure drop is caused because of the inlet nozzle, and the tube bundle and etc. they are not causing any pressure drop at all. And again, outlet nozzle causes 31% of the pressure drop, right? So it is like 100% of the pressure drop is caused by the inlet and outlet nozzles. So these are some of the inferences which you can draw out. Again, okay, so 46 is the temperature outlet which we wanted to decrease, right? So again, I will go here, again I will click here, tubes. Let's say now the tubes are 40 tubes. I will again run it. We will see what is the effect of it. See, the temperature got down, right? But I have also decreased the number of tubes. Because of that, the uh, the exchanger geometry should also get changed, right? So that is here in setting plan, etc. But you will find that the number of tubes are 51 still. So that is one of the, I think, drawbacks here. So for this particular thing, I need to reinitialize it by opening this particular here option here itself. I will again run it. So it will now again generate the results, but this time it will show me the less number of tubes. Okay, see the number of tubes are now, I don't know, but yes, it should. Okay, so it says that number of tubes are again 51. So I need to, in this case, I need to see what is warning. So in warning, it says that the tube count from tube layout is 51, which differs from the effective tube count of 40 which you input, right? Because the shell ID, because in this particular design, the number of tubes are governed by the shell ID, which is this, right? Which is this shell ID you can see here, uh, or I mean, we can also see here what is our input shell ID, right? So it is 8" or 205 mm. So the number of tubes are particularly governed by this shell ID, right? So I'm supposed to reduce that shell ID so that the number of tubes will also be decreased, of course. But for calculation, the number of tubes are 40. The number of tubes are 40, but for the setting plan and for the tube sheet layout, the number of tubes are right now they are also 51. So I need to decrease this shell ID such that I will get that reduced number. So we can do this exercise offline, right? Okay, now I will but before just closing, there is one very important thing which I wanted to show you. Now that EDR file which is there, this EDR file, right? Because everything is in this EDR, right? This option itself says that it is EDR browser. But where is that file which we have saved, right? So I will first of all save this to show you where is that file. I will save it on desktop saying heat exchanger, right? Okay, I have saved it, heat exchanger. And if you will see here, heat exchanger, right? This is a particular file. So in order to see that file, I will have to close it, file, and I will have to again open it. So we know that when Aspen plus file opens, there is a folder which automatically opens, right? All its backup files are there in that particular file. So if you go here, so on the desktop, if you will go in on the desktop, I am trying to actually minimize it. Okay, if you will go here, you will find this particular folder in which B11, the name is B1 underscore 1. That is a particular file which is of Aspen Exchanger and Design extension, right? Because that is .edr, right? So we can close it. Once, if you will close this file again, that folder which was generated will automatically disappear, right? So if you want to use that file, you have to open this particular file, that is compound file, Aspen plus compound file. Then the folder will get generated. You are supposed to copy that and you can keep it for your reference. Okay, so that is how you can do it. I hope you understood what I wanted to convey you. Please post your comments if you want to say something or if you will have any doubt under the video. Thank you very much.